Hello everyone, I'm Michele, Early Stage Researcher 1 in TeraApps project. I'm Italian from Rotondo and after my master degree in electronic engineering at Politecnico di Bari, I moved to University of Glasgow for my PhD. Today I will try to explain in simple words my work on resonant tunnel diodes, epitaxial wafer design, manufacture and characterization. This project is funded by the European Community and is also part of the Horizon 2020 program. Let's begin with the research scenario. In this picture, a wide range of frequencies is considered, and moving from the electronic side to the photonics one, we have several applications. In terms of communication, higher frequencies simply mean more speed. As an example, we can consider the fiber optics broadband. In the electronic side, for a wireless point of view, we are stuck here. The reason is simple. Increasing the frequency, we cannot reach the minimum required power. The power drops. So here the real problem. The global wireless data demand is increasing year per year and we are suffering a lack of technology that can operate in the terahertz spectrum. So the goal and the output of the project is to improve the resonant tunnel diode output power to obtain a terahertz source suitable for the market. An RTD is a nanoelectronic device. What nano means? If we consider a human hair diameter of 16 micron, in comparison, this is an entire RTD device. And again, if we consider its active region is even smaller, its dimension is comparable with the DNA one. Let's now consider a double barrier structure like this. If we launch an object to the barriers, it will be rejected, and this is an intuitive concept. At the nanoscale, we are working with quantum physics, and in some particular condition, the object cannot cross the barrier, and this is called tunnel effect. In reality, and electrically speaking, things are a little bit different. We have electrons that want to cross the barrier, and applying a voltage to our device, we can reach the resonant condition, and at the end, the entire IV characteristics. RTDs are made from semiconductor wafer that are composed by different layers of different material with different physical and electronic properties. As an example, we can consider three elements A, B, and C. They can combine together to obtain a new structure, characterized by a lattice constant K. When together, each layer has to match the lattice constant of the substrate. For this reason, we can observe some stretching and some relaxation. The process to obtain this wafer is very complex and it's called molecular beam epitaxy, in which different elements are inside separate chambers. A molecular beam is obtained and directed on an out substrate. And layer by layer, our wafer is finally grown. From the wafer, we can obtain our RTD device after several processes in cleanroom. At the end, the characterization process is the one that helps us to determine the device performance and the material quality. As an example, we can use a very powerful microscope to observe the double barrier structure. As we can see in this picture, the first barrier is not as good as the second one, and this condition can compromise the device performance. Another interesting way to characterize material is the use of a photoluminescence spectroscopy, in which we use a cryostat to reach a very low temperature, in which samples are put inside a particular chamber, and we use a laser to characterize the electronic properties of the material. As outlined, I presented the most intuitive part of my work, in which essentially we use the characterization data as a feedback for new epi design, but there are several other elements that we need to consider, like simulation, device design, and several other techniques of characterization. In conclusion, RTDs will help us to speed our communication system, but terahertz sources are also important for several other applications like security scan, radar and satellite communication, astronomy, pharmaceutical application, and biomedical diagnostic. Hope you enjoyed the video. For more information, visit our website and watch the other video made by my colleagues in this project. Thanks for your kindly attention.